Hi, in this video, we want to take a look at longitudinal models in item response theory. All right, so remember, in item response theory, we're talking about using under the hood latent variables to model the performance on individual questions on like a test or a survey or a questionnaire of some form. Now, for this video, we're interested in longitudinal aspects. So what's happened is that we have the same test, the same survey, the same quiz, and we give it multiple times. And we're interested in how things progress over time. You know, see if the subjects getting better at the test, are they getting worse? And, you know, we can use this to get an idea of how well is their overall proficiency increasing. You know, and, you know, so something about this is that we're going to be using the same questionnaire, the same survey, the same test multiple times with the same subjects. All right, so this is a modified example from Modern Psychometrics with R, and it's a Springer book, and here's the GitHub page for the data and the code. All right, so for this example, we're going to use the work design questionnaire for our package authors, and data frame of just over 1,000 individuals, 18 items, and we've got these guys are the classifications of each of the questions. And if we look at the original data, it's labeled 22 through 39 so that we know which one corresponds to which one in this. And we're going to be looking at the SDO wave is what it's called in MPsychoR. And for later on an example, we're going to use a covariate to see if a particular covariate could be included in a model and if that's worthwhile. So I'm going to go ahead and call that group. This is, for the moment, we're not going to use it, but we will in an example later. Now, when we use it, we have to have integer values, and our group has to start at 1. So I can't start at 0. When I initially made the vector, it started at 0, and I got an error like, hey, it needs to start at 1. So just something to be mindful of. And so then later on, I create, or I use, not later on, I index the subjects by their row number, because in the data set, each row corresponds to one subject, and then I group the subjects together by the grouping covariate. Now, the grouping covariate is their overall average above or below the median. Kind of a stupid covariate because that's not one that we would have independent of the data. This is why you'll notice I call it a fake covariate for demonstration. We wouldn't actually be using this. All right, so something I want to do, I want to visualize the data because I want to get a feel for what's going on. I want to see what's up. And so I'm going to use ggplot. And if you look at the original data set, it's in wide format. Now, if you work with ggplot, you know that it prefers to have long format. So I need to do some conversion. I'm going to use the gather function in the tidyr package. And so if you look at the original data set, each item and year is the header of each column. So it goes, you know, the question, item, and then the year it was given, and then we have each subject corresponding to rows. And so to make sure that I preserve the row information, I tack on 1 to n, and so that this new column records where or which subject does the score correspond to. And then when I convert from wide to long, I have item year telling me, that column tells me which item it is, which year it is, and then I have a separate column for the score. So previously, each item and year had its own column. When I'm in long format, now all of them are all the scores are stacked on top of each other, and I have a special column to tell me where did I originally get that number from. And then I go ahead and I extract the item from the item year column. And here I'm using string extract from the Stringer package. And I do the same thing for the year. Easy peasy lemon squeezy. So items are I1, I2, I3, I4. Years go 1996 to 2000. And I'm using regular expressions to extract them. And then I go ahead and tack on that group covariate that we talked about a moment ago, and I just label above or below average using that. And something else I do, and this is what the author of the textbook did. I don't know if it's really that needed, but I couldn't disagree with it when I was looking at it. I was like, I wouldn't have done it personally if I was leading the project, but I don't disagree with it either. So I went ahead and went with the author's choice of any value that is above 5, I reduce down to 5. So the scale goes all the way up to 7. So any value of 6 or 7 was muted down to 5. Now, why do we do this? This is good practice when you have skewed data and you know that an observation will pull on the rest of your model more than you want it to. And so here I was like, okay, I'll do that. I can see why he did it. There might be something I'm missing. It might be the most intelligent decision ever. I don't know. Go along with it because definitely not a bad decision. All right, so now to go ahead and make the plot, I'm also going to use ggplot and ggally. This is good for labeling. All right, so something I want to talk about in this plot here. It gets kind of warped because I'm using R Markdown, but if I was to save this as a PNG file or a PDF, I can make this look really, really sharp. And this is what I do professionally at work. Notice that every single item is labeled. I label everything. Why? That way, if I have someone who's not really familiar with mathematics, not comfortable with bar plots, they don't have to judge things. They can actually look at the hard numbers. This is a very important thing. This is one of the biggest shortcomings of data science, in my opinion, is that we make visualizations and we don't label things properly. Label it, label it, label it. Now here, since I'm in R Markdown, you see it's very, very crowded, but when on my machine, this was not crowded. If you run the code, if you go through and you copy this down and post it, you'll see that this is it'll look like pretty good. It's a pretty good plot. So some stuff that I did with this. So with my label, not only did I label everything, but also if it's a very small proportion, very small amount, I went ahead and just omitted that label. Why did I do that? Well, if you look down here, you notice that there is like a little bit of blue in that below that 41, but it's such a small amount that the number is going to overlap with that 41. It's going to be crowded and it's going to be hard to see. So a good practice is when you have very small proportions, don't label that because it will just befuddle the visualization. Something I like to do, I like to actually put a color box around my box, the bars of my box plot. So you see that I have black around here. A lot of times what I'll do is actually I'll go with white. And so that helps distinguish the different portions of the bar nicely. Looking at this now, I think I probably should have gone with white, but whatever. I find that putting things halfway into their position is usually a good way to go because putting it halfway tends to prevent overlap. And the faucet grid makes it so that we can see the year and item nicely. Now, with the group aspect, this kind of gives me an idea of how well does it correlate with the rest of the data. So something that jumps out at me is when I look at I3, you see that I've got blue kind of like going all the way to the right. But when I look at I2, blue is strictly on the left. So we can see if blue is strictly on the left, it's probably going to be correlated more with the overall performance. So that's just something to be mindful of as I perform my analysis going forward. All right, so we can do a linear logistic model for measuring the change. And so what we're going to do, we're going to use the person parameters to evaluate changes in the subject. And what we're going to really be doing is we're going to be using design matrices to specify what our model structure is. And we're going to use this as a way to control the levers of that model. All right, so before I do this, I'm going to go ahead and convert the data to binary. So if the value is greater than the least value of 1, it's a 1. If it is equal to the least value, then it's a 0. So 0 means it's the lowest value possible. 1 means it's greater than the lowest value possible. And this makes sense as we see that we have the bar plot where the most frequent observation is always the lowest value. All right, so let's get a baseline linear logistic model. And so remember that each year is a measurement point for us. So when I do that I have a measurement point, I have 5 different years, 1996 to 2000. And I'm going to go ahead and I'm going to use the ERM package, which is usually used for rash models. And I'm going to build the model. And I just, so I pass the data and I say, hey, I've got 5 measurement points here. Okay. So now it's going to go ahead and build the model. Now, something that's nice about this package is it actually detects features of the column names for us automatically. And you'll notice that I have item 1, item 2, item 3, item 4, and so on. And you'll notice that instead of having 1996, I have T1. Instead of having 1997, I have T2. So the package automatically detected features of the column headers for me. That way, if I'm coding my column headers in the manner that the package likes, I don't have to do any further work. It's easy for me. Now, remember that whenever we're doing a logistic regression model, which these models are just extensions of logistic regression, I always have like a linear algebra aspect going on to this. And I always need to be mindful of that. And we can see it in our design matrix. And so here we can see that we've got like these 3 negative values, then all zeros. Then we have just the 1 by itself, then zeros, then a 1 over, and then the 1 over. And we can see that we have all zeros in this block. And then here, these 4, if I look at just the 1996 rows, these columns add up to 0. All right, well, now let's go down to 1997. And so here, I see I have the same block here, but for ETA 4, I'll have all 1s. When I go down to 1998, I see I have the same pattern on the left, and then I have all 1s over here. Yeah, so this design matrix is being computed based off of the linear algebra aspect of the logistic regression model. It's not 100% correct for me to say logistic regression, but that's how to think about it. Don't get mad at me. Don't hate me in the comments, please. Go ahead and hate me. Just do whatever you want. And so, we see the pattern again. Okay. Well, let's take a look at the results. And we get parameter estimates. So we have, ETA 1, 2, 3, 4, all the way up to 7. And you'll notice I've got 7 columns in my design matrix. And we go ahead and we get easiness parameters estimates off of this. And in this package, it calls that beta. So eta is one parameter and beta is another. And then we'll also have the individual factor, the latent variable involved also. All right, so now what I want to do, I want to control the model structure with using the design matrix. All right, so what I want to know is, do I need these other values going on? Clearly, we can see a difference in the left side and the right side of the design matrix. Do I need eta 4, eta 5, eta 6, eta 7? Do these add value to my model? All right, so what I want to do, I want to consider the model with only these 3 parameters, and I want to consider the full model. And I want to see, are they equally informative? Should I go with the reduced model if they're equally informative? Should I go with the more complicated model if they're not? And so what I'm going to do, I'm going to take that matrix that we were just talking about, we were just looking at, the design matrix, but I'm going to reduce it down to the first 3 columns. So remember, this is the one that has the negative values appearing corresponding to the first row of each year. Okay, so now I'm reducing the model structure with the design matrix, and then I go ahead and fit it. And now let's go ahead and take a look at the summary, just so I can see what's going on. So I can see that now I have fewer basic parameters modeled. I see that I still have an easiness parameter across the board. And now I can do an ANOVA test to see, are they equally informative? Okay, so if the null hypothesis is that they're equally informative, I'm going to use the simpler model structure. If I see that there's a difference, I'm going to go with the more complicated model, the one with the bigger design matrix, the one with 7 parameters, 7 ADAs being fitted. And so we reject the null hypothesis in favor of the alternative. So we conclude that they are not equally informative. That means that one of them is more informative than the other. Well, they're nested models, so the more complicated one is more informative. So the first one with more parameters is what I would prefer to use. All right, so now let's go ahead and mix it up. Let's go ahead and add a grouping covariate to our model. And what we want to do is, including this covariate in our model, does that improve it compared to the baseline model? So once again, if the covariate adds, if I get informative value greater with the more complicated model, I want to keep the more complicated one. If they're equally informative, I want the simpler version. All right, so I'm going to do the same thing I did for the 5-point model, but I'm going to add a group covariate. So notice that this group is outside of my data frame. It's floating around someplace else. This is not part of the items. Here, I'm entering only the questions, only the items that are being involved in the analysis. And here, this is a covariate that is outside of the items. Now, for this example, remember the group was is above or below the sample average for the row average says. And so it's kind of a stupid covariate to be using, but I just want us to see that this is how I would proceed if I wanted a covariate. All right, so here we can see that we have our basic parameters, but this time we have an 8th one going on. We have another one there. So instead of having 7, I have 8. Then once again, I get easiness parameters, but there's a kicker to this. I've got the G1, G2. Remember, the G1, G2 is another parameter for us. And so I can see that this item easiness matrix has grown, it's in fact doubled in length. All right, so now I want to ask, are these equally informative? Which one should I use? All right, so I've got 3 models, so I'm going to pass all 3 into ANOVA, and I'm going to check it out. So now what this is going to do, ANOVA will automatically figure out which one's the most complicated and which one's the least complicated and put them in order. Now for this, they have to be nested models. In other words, the only difference between them is basically, if I take the most complicated one and I remove a parameter, I get another model. If I remove a parameter, I get another one. So that that's what we mean by nested. And so I went ahead and I sorted the models in the order that they appear. But if I didn't pass them this way, let's say I permuted this chunk of code, I switched the order of the rows, the ANOVA function would figure this part out, that model 1 would still be model 1 regardless of the order I put them in. Now, for reader ease down the road, let's say 6 months, I go back to my code, I want to see what's going on. I always try to make things consistent. So you'll notice I put the most complicated, or the one that is row 1 here, row 1 here, row 2 here is row 2 here, row 3 here is row 3. That way when I start like digging through, it's easier to spot what's going on. All right, so we can see that the difference between model 1 and model 2 is statistically not significant. So adding the group covariate to my full model does not improve my model. So I would not want to include that. I would not want to include the group covariate. Now, when I look at the difference between model 2 and model 3, I see that there is a statistical difference, which we already concluded previously. But you'll notice that the p-value has changed. That's okay. It's a slightly different hypothesis test. All right, so now we want to take a look at linear logistic models with relaxed assumptions. So here I'm doing things very similar, but now instead of LLTM, function, I'm using LLRA, log or linear logistic relaxed assumptions. And things pretty much work out the same way. It's just that I know that my assumptions are weaker. Remember that, so when you're dealing with statistics, if I have very little data, in general, I need more assumptions to be able to reach a conclusion. If I have a crap ton of data, I don't really need a whole lot of assumptions. So if I was like short on data, maybe collection is very expensive, then I would not want relaxed assumptions. Now, I have to use subject matter knowledge to know if the assumptions are appropriate. And so things pretty much just run similar to like the first model that we got. Now we can also do a two-tier approach to the longitudinal models. Now here what we're going to do, we're going to move into a different package. We're going to use the MERT package. Remember, MERT is multivariate. And so that's a big difference. Now MERT has a lot of flexibility. It has to the point where it's like it's too much to deal with. So this is a very comprehensive, very powerful, very specialized package for working with stuff. To the point where it might be, I feel like it might be overkill for most people. But let's go ahead and proceed because I like digging in. All right, so something I do, I go ahead and I get my data, and any value greater than 5, I convert to 5. So values of 6 and 7 are reduced to 5. And the reason why I do this, again, is so that extreme observations do not pull on my model more than others. If you think about leverage in regular multivariate regression, regular regression, you know that leverage reflects how much something pulls. The farther away it is from, the farther an observation is from like central tendency, the more it gets to pull on the rest of the model. And so doing this prevents that pulling aspect. All right, so now in the MERT package, what I'm doing here is I'm saying columns 1 through 4 correspond to the 1996 factor, latent variable, or estimate of the latent variable. Columns 5 through 8 correspond to the 1997 factor. Columns 9 through 12 correspond to the 1998 factor. 13 through 16 corresponds to the 1999 factor. And then our last columns correspond to the 2000 factor. Now, I don't have to have the, like here, you'll notice I went 1 through 4. I could have also, if I want to, I could go 1, 2, 3, 4. That would also work. I can, so I do not have to have consecutive columns to do the matching up. Now here, I'm telling MERT which variances and covariances to estimate. So if I want a variance, I just go ahead and I put a factor with itself. If I want a correlation, I take a factor and another factor and put them together, and it will compute the correlation there. Otherwise, it'll make assumptions off the model structure what it will be. Now here, this is the mean is declaring which factors get to be freely defined freely in their mean. Now the constrain parameter, what this is saying is that the variables for here have to be the same. So we want the same intercept. Okay, so actually I need to back up on something. Remember that A in the MERT package, A corresponds to slope, D corresponds to intercept, G corresponds to guessing parameter. Okay, so here we're not doing anything with guessing, but we have slope and we have intercepts. All right, the intercept for 1, 5, 9, 13, and 17 items, so these are all item 1 over different years, the intercept needs to be the same. Once again, I'm saying the intercept for item 2, so here, these are the columns for item 2 over the 5 different years. These are the columns for item 3 over the 5 different years. These are the columns of item 4 over the 5 different years. We're saying that the intercepts for all of these have to be the same every single time. And what we do to define the model, we actually define it as a special character string, and then we pass that character string to the MERT model function. And this, as long as I've written everything incorrectly, the function will figure out what is the actual structure of the model. It'll do it very nicely for us. Now, something that's important to notice is that each row does not have a comma. If I'm putting in a comma, that is telling MERT that I'm still within the same parameter. You'll notice that here I do not have a comma, don't have a comma, don't have a comma, don't have a comma, don't have a comma. At the end of each row, at the end of each parameter, say at the end of each parameter, I do not have a comma. And now we want to use the bivariate factor function to go ahead and do the analysis for us. I need to tell it the data. I need to tell it the default model. So the default model, I'm saying, you can see I'm using the rep function 5 times. So this goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. All right, so I have 1, 2, 3, 4 repeated 5 times. This is saying that I have item 1. So item 1, item 2, item 3, item 4. Start over item 1 for the second year, item 2 for the second year, item 3 for the second year, item 4 for the second year, and it repeats like that. And then this is where I get more nuance in the actual model structure. This just says basically how the relationship between the different columns. This says specifically how I want to structure that model. And this says to estimate the standard error. Now I made a mistake. I made a mistake and I regret it. I did not put for verbose equals true. And so in a moment, we're going to see a lot of output, which is, I feel like, is not really that useful. Well, the end result is useful, but the next couple of lines are not. All right, so here we see a bunch of iterations. And there's a bunch, so it gets down to 70. Okay. And so we can see that it converged within 70 observations. All right. And model likely not empirically identified, that is likely to happen anytime that I have preconceived notions of what the model should be. If I'm using what the data says the model should be, like an exploratory factor analysis, then then this warning most likely would not come up unless I've got crappy data. All right, so now we can look at our model and remember that A corresponds to slopes, D corresponds to the intercept terms in our logit model aspect. That's not quite 100% correct, but go ahead and run with me. And you'll notice I have A1, 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 A1 are all 0.85. And then I have A6, A7, A8, A9 are non-zero values. So we can see that here, all of these are 1996, and all this is going to be item 1, item 2, item 3, item 4. Now you'll notice that I don't have a 10th A. Why is that? Remember that we always have this whole linear linear algebra aspect to our models. I have to have a baseline level, and I'm missing A10 because of that baseline aspect. Now I have D1 through 4 because we said that D1, D2, D3, D4 have the same aspect for every single item on the test. Oh, something I want to take a look at, I want to point out. So here's item 1, and I have 0.44 for A6, but I have 0.56, and this is because we have freedom in what this is allowed to be. Now, when I get down to 1997, I have 0.85, 0.85, 0.85. You see that it's constant down the list like that. And then I have the same pattern of A6, A7, A8, A9 are non-zero. Oh, and something I need to point out also, I have 0.14. Okay, so if I look here, 0.14, and I go down here, 0.14, negative 0.97, negative 0.97 on the 1997, negative 1.7 D3, negative 1.7 D3, negative 2.8 D4, negative 2.8 D4. This comes from how we specified the model. And we can, keep on looking at it and see what we've got going on. And then we have our group parameters. And so here it's really just focused on the variance. So now the order of the covariances are like in reverse order. So you'll notice I have 1, 2, then 2, 1. It's ordering by the second digit first and then the first. Then 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1. Now it gets to the 2s like that. 1, 2 is represented by 2, 1. So it goes to 2, 2 first. And now we can take a look at latent growth item response models. Now here is going to, I'm using the MERT package once again. I'm going to be using MERT model, but how I specify things are very different. So here I have the same constraint on the intercept terms. I'm going to say that the intercept and slope are being have input from all columns. My covariance is going to be all the possibilities off of these 3 factors. We're letting the intercept and slope have free mean. Now, something that's important is I'm trying to specify a starting value for these, and then the fixed is saying this is an actual fixed value. Do not actually estimate this. And so I use the MERT model to take that character string and put it in. And then I use the B factor to actually fit the model. And you'll notice that once again, I'm saying how the columns relate to each other as the same items appear over different years. I specify the model using that character string and MERT.model, and I do fit the standard error. Now, I get some output about the iterations, and you notice that it's a bunch. It's a lot. It's still going, still going, still going, still going, still going, still going, still going. It's almost done. Almost. There we go. All right. So the cycle's terminated after 500 iterations. What this is saying that is after 500 iterations, the system did not reach the criteria for convergence. So this is a sign that we do not have a good model fit as is. A good rule of thumb when it comes to data, if it takes more iterations to fit, that's a sign you have poor model structure for your data. I would not trust this model as is. Now, I could run statistics on it, and the statistics may say it's good, but if it doesn't converge, that's a sign that I have contradictory signals within my data. If I have contradictory signals in my data, I probably do not want to work with it as is. And so we can take a look at the coefficients, and you'll notice that A1, A2, A4, 5, and 6, that these slopes are being treated as fixed values. I don't have like an estimation on them. A3 does here. A4 is free. A5 is free as a variable. And then A6 is free as a variable. And then we can see that our intercepts are free also. Also, you'll notice that on the intercepts, I get the same value in 1996 as I do in 1997 because of that constraint parameter that we put in. And this is pretty, so I mean, a lot of stuff to look at. It vomits out a lot of stuff, but if I'm interested in this and I want to roll up my sleeves and really dig into it, it's here for me. It's up to me to get, get crazy, get nuts, and start digging in. Well, I hope you enjoyed this video. Take care and goodbye.